Okay, just really quickly, summary, steel, aluminium metallurgy for aeronautical. If you look at steel metallurgy, if I slow cool steel, I get ferrite and cementite coming out as proeutectoid ferrite, as in ferrite grains, and what's left becomes perlite at 723 degrees. I'm assuming, of course, it's between 0.3 and 0.8%. However, if I fast cool it, I snap freeze the austenite into a metastable phase called martensite, which isn't on a phase diagram because it's not equilibrium. Steel does not want to exist as martensite. Nature says it wants to exist in two separate phases, cementite and ferrite. So, martensite, if you heat it up, I'll go over here, high temperature austenite. Take two, apologise for the little hiccup. High temperature austenite, when you cool it slowly, ferrite precipitates out on the grain boundaries. Base centicubic high temperature turns into body centicubic low temperatures, precipitates out on the grain boundaries. Everything that's left at 723, the carbon-rich austenite, transforms into a lamellar structure of ferrite and cementite called perlite. Slow cool. Fast cool, above 0.3%. You quench it, you get martensite. This is one particular form of martensite, which the textbooks in the New South Wales HSC syllabus use. It's acicular, it's needle-shaped. Just draw that if you're asked to draw the structure of martensite. It's body-centered tetragonal. It's snap-frozen in a phase it does not want to live in. If you give it a bit of heat, 400 degrees times 10 seconds, 200 degrees times 1 hour, it precipitates out as a fine network of iron carbide, Fe3C, in a lattice of ferrite. That's precipitation hardening of steel. Precipitation hardening of aluminium happens exactly the same way. Aluminium copper, at 550 degrees, it holds up to 6% copper in solution in aluminium. If I cool it slowly, slow cool, I get copper aluminide precipitates forming on the grain boundary. And then when it hits low temperatures, everything that's left turns into a copper. Slow cool, equilibrium cool, where nature does what it wants. However, if I fast cool this, quench it in water, heat it up to 550 degrees, drop it in a bucket full of cold water, atoms can't move in time. It does not form this. Same when I quench steel. Atoms cannot move to make two phases. It just snap freezes in wherever it is. Here in steel, it distorts the lattice. Here it just basically creates a stressed copper aluminium solution. 100 degrees centigrade times 1 hour produces copper aluminium precipitates all through aluminium. That's the basics of precipitation hardening. One thing I forgot to mention, this was the World War I German military secret. Like every metallurgical discovery, it was essentially a black art. A researcher in Germany in the early stages of World War I was trying to find out how to make aluminium stronger. He added copper, tested it late on a Friday, it was weak, went home for the weekend, came back Monday and it was strong. Scratched his head, wondered what happened, repeated the experiment and the same thing happened. Day one, this is soft and malleable. 4 days later, it's strong and tough. That's why aluminium and copper alloys are still used in aircraft. You can form them in this and they need minimum energy. They're malleable, they're soft, they're formable. 4 days later, they're strong because of the change in phase.